So, good day everyone. Now we're going to discuss sharing stress. So, sharing stress is a type of stress that occurs when forces act parallel to a surface. These forces cause one part of a material to slide over one another. So, sharing stress is also called tangential stress, because the force acts along parallel to the surface. So these are the two different types of stress. First, the tensile and the compressive. So the tensile is a pulling force and the compressive is a pushing force. So ang pasabot ng tensile is pakuha nimo if imong given is birahon or i-pull nimo man na siyang tensile stress. Yung compressive stress is i-compress nimo imong iduot mo na siya ang compressive stress. So next, the sharing stress formula. So tau or T is equals to V over area. So the T here is called sharing stress, or it's called tau. And the V is sharing force, and A is area being shared. So the unit of tau or T, or it's called sharing stress, is Newton per millimeter squared. And the sharing force, the unit is Newton. And the area, or the area being shared, the unit is millimeter squared. So let's go to next. So these are the two types of shear: the single shear and the double shear. So first, the single shear is the only one surface resists the force, or the one load path, but more shear at each failure plane. And the double shear is the two surfaces resist force, or the two load path but less shear at each failure plane. So, ang kani nga diri, as you can see the picture, ang kani siya, kani tawag kani is mo ni ang load, kani mo ni ang load, kani sad mo ni ang load, kani mo ni ang load. Niya, ang tawag ani kani nasa tunga, kani siya lang. Kani siya, ang tawag ana is the failure plate. Okay? Tawagan niya kay failure plate. So, if matawag na siya og single shear, kay isa ra man ka area ang pangitaon. So, ang pangutana, asa pangitaon ng area? So, ang pangitaon ng area is ari na pangitaon kani, which is mao ni kaning circle, mao na ang pangitaon ng area. And nganong gitawag og double shear is duha man siya ka area ang kwaon, kaning babaw o kaning ubos. Okay, gets ra? So let's proceed sa sample problem. Okay, here. So a pin carries a load of 2000 Newton and has an area of 100 millimeters squared. So find the single shear and the double shear. So, okay. This is the formula that we use to find the single shear and double shear. So the single shear is put the given is the load is 2000 Newton and the area is 100 meter. So we all know that the V is the load. So put the 2000 Newton and over the area is 100 millimeter. So 2000 Newton over 100 millimeter is equals to 20 Newton per millimeter squared. And next, the double shear. So since double shear man siya, ang area niya is duha. Diba? So you can put the 2000 Newton over the shear is 2 and times 100 area. So 2000 Newton over 200 area is equals to 10 Newton per millimeter squared. So that's all, and here are the practice problem. If ganahan ka mag-practice is nara ko'y gahatag. And that's all. Thank you.
Good day everyone. So I'll be discussing the introduction of strain. So introduction of strain is in the study of mechanics of materials. Strain is one of the most fundamental concepts. It provides a quantitative measure of deformation in a material when subjected to external forces. Strain essentially describes how much a material deforms in relation to its original size and shape. The study of strain is crucial in engineering, as it allows engineers to predict the behavior of structure and mechanical components under various loading conditions. Definition of strain. Strain is defined as the ratio of change in dimension to the original dimension of a body when subjected to stress. It is a dimensionless quantity because it is a ratio of two similar quantities. So strain is essentially a way to measure how much an object deforms, like stretches, squishes, or twists, when a force is applied to it. So think of a strain as a percentage of change. If you pull on a rubber band, it gets longer. Strain tells you how much longer it got compared to its original length. Because it's a ratio comparing the change to the original, it has no units like inches or centimeters. It is just a number that represents the intensity of the deformation. So mathematically, it expressed as strain is equals to change in dimension over the original dimension. There are types of strain. So there are several types of strain depending on the mode of deformation. So number 1, normal strain. This is the change in length of a body when subjected to axial load. So there are two types of normal strain. So the first one is tensile strain. So tensile strain is stretching something out, make it longer. And then the compressive strain is pushing something down to make it shorter. The second type of strain is the lateral strain, the strain that occurs in the perpendicular direction to the applied load. So think of a piece of gum. When you pull it to make it longer, the middle part gets thinner. So that thinning is lateral strain. The third type of strain is the shear strain. This is a change in angle or tilt. So imagine pushing the top of deck of card sideways while the bottom stays still. The card lean at an angle. That leaning is the shear strain. The fourth type of strain is the volumetric strain. This is a change in total volume. So think of a squeezing a sponge in your hand from all sides. It gets smaller overall. That is a volumetric strain. So we have a problem here. So a steel rod with an original length of 2.5 meter is subjected to a tensile pulling force. After the load is applied, the rod is measured to be 2.504 meters long. So I'm sorry, I forgot to put the question on the problem. So the question is calculate the normal strain in the rod. So the solution will be this. So first is identify the given values. So the original length is the 2.5 meter and the final length is the 2.504 meter. So first we'll be finding the change in length. So finding the change of length is, the formula of that is change in length is equals to final length minus the original length. So 2.504 minus the 2.5 so is equals to 0.004. And then calculate the strain using the formula. Strain is equals to change of length over the original length. So it's 0.004 meter over 2.5 meter. So it equals to 0.0016. So the strain is 0.0016 or 1.6 times 10 raised to negative 3. So that is our strain for that problem. So let's move to the second problem. So a steel wire with an original length of 2.0 meter is subjected to a tensile force. After the force is applied, the wire stretches by 0.25 centimeter. Calculate the longitudinal strain in the wire. So this will be the solution. List the unknown values and ensure they are in consistent units. So the original length is 2.0 meter. And the change of length is 0.25 centimeter. So as you can see, they have different units. So the change of in length will be converting this into meters. So 0.25 meters is equals to 0.0025 meter. So apply the strain formula. So substitute the values into the strain equation. So we all know the strain formula. So strain is equals to change of length over the original length. So strain is equals to 0.0025 meter over 2.00 meter. So the strain is equals to 0.00125. So the value of strain on this problem is 0.00125. And that's all. Thank you.
Good morning, everyone. Today, I will be discussing about the fundamental of deformable bodies. Before we start, I want to introduce myself. I am Jofel A. Canoy, and the instructor for this subject is the engineer Jigs Oteda. So, fundamental of deformable bodies is also called mechanics of deformable bodies or strengths of materials. It is a branch of mechanics that studies how solid objects deform and respond to applied forces, beyond just their motion or equilibrium, which is the focus of rigid body mechanics. So let's proceed about the axial deformation shear stress diagram. It is the change in length of a member when a force acts along its axis. The center line of the object, the force can either stretch or compress the material. So, just like the picture here, this is what we call tension, or it elongates the objects or material. And here, this is compression, or the member shortens. Let's proceed. So we have formula. This is a axial deformation or change in length. Change in length is equals to axial load or force applied times length over area times Young's modulus, or this is constant, or it depends to the problem given. And we have formula here, two formulas here. Deformation due to weight. We have change in length is equals to weight times length over 2 area times modulus. So when we use this formula, so if the problem has a weight, so we can use this formula, or it's either this. So we so let's proceed to the problem. Problem number 1. A steel rod having a cross-sectional area of 300 millimeter squared and a length of 150 meter is suspended vertically from one end. It supports a tensile load of 20 kilonewton at the lower end. If the unit mass of steel is 7,850 kilogram per cubic meter, and the Young's modulus is equals to 200 times 103 Newton per meter squared, find the total elongation of the rod. So just like what I said earlier, we can use this formula when the problem is given by a mass or density. So the mass of this problem is 7,850 kilogram per cubic meter. So, and the unknown is the elongation of the rod. So let's going back to the formula. Here we can use this formula because the given has a density or mass. So the pressure or force applied in this problem is here 20 kilonewton, where K is 10 raised to 3 times the length of the material, which is 150 meter, over the Young's modulus, which is 200 times 103 mega, which the mega is times 10 raised to 9, times the area, which is 300 millimeter squared. Since the area is millimeter, we should convert this into meter. So here, this is also already converted to meter, plus the density, which is 7,850 kilogram per cubic meter here, times gravity is 9.81 times the length of 150 squared, over 2 times 200 103 here. So if you input this in a calculator, we got this answer, 54.3 millimeter. So let's proceed to the second problem. A 4 millimeter diameter steel wire, 3.2 meter long, carries an axial tensile load P. Find the maximum safe value of P if the allowable normal stress is 280 megapascal and the elongation of the wire is limited to 4 millimeter. Use E, or Young's modulus, 200 gigapascal. So let's analyze the problem. Since the problem is given by diameter, so the area of this, we can use the area of the diameter, which is pi times 4 squared over 4, since this is 4 millimeter. So we got 12.566 millimeter squared, and the formula for pressure is stress times area. Since we have stress 280 megapascal, and the area is we got earlier is 12.566, we get 3518 newton. And the unknown value is find the maximum safe place. So the formula for this is equals to elongation times Young's modulus times area over length. So since the value of this unknown formula is already we already have we or the value is already given, we or if you put this into a calculator, you get a 3,140 newton. So therefore, the maximum safe value is 3,140 newton. So that's it. I hope you understand my topic. Yeah, that's all. Thank you.
Hello everyone. In this presentation, I will discuss working stress and factor of safety. These two concepts are used to make sure that materials are used safely and do not fail under load. They help in setting limits and adding protection when materials are used in real-life situations. Working stresses. Working stresses, also called allowable stress, is the maximum stress that a material is allowed to carry during normal use. This value is always lower than the material's actual strength to make sure it remains safe even when conditions are not perfect. It means that working stress is the safe amount of stress that a material is allowed to carry during normal use. Even though a material can handle more stress, it is not used at its maximum strength. This is done to avoid failure in case of unexpected conditions like higher loads or small defects. Working stresses formula. Working stress is calculated using the formula working stress is equal to ultimate strength over factor of safety. This formula shows the safe limit of stress that a material can carry. Using a fraction of the material's full strength helps prevent failure under unexpected loads or material defects. So, the working stress formula shows how to find the stress limit of a material. It is calculated by dividing the ultimate stress by the factor of safety. This means only a portion of the material's full strength is used to ensure safety. Factor of safety. The factor of safety is a measure of how much stronger a material is compared to the stress it actually experiences. It acts as a safety margin that protects against unexpected loads, materials defects, or changes in conditions. A high factor of safety means the material can withstand much more stress than what is applied, while a low factor of safety indicates the material is being used closer to its limit. So it means that tells how much stronger a material is compared to the stress it carries. It provides extra protection by making sure the material is not used too close to its limit. Factor of safety formula. The factor is calculated using the formula factor of safety is equal to ultimate strength over working stress. This formula tells how many times stronger the material is compared to the stress it carries. It is essentially the inverse of working stress formula. So the factor of safety formula shows the relationship between the material strength and the stress applied to it. It is found by dividing the ultimate strength by the working stress. This helps determine how safe a material is under a given load. So here, we have two sample problems of working stress. Problem number 1. A steel bar is subjected to a load of 90 kN and has a cross-sectional area of 300 mm squared. If the factor of safety is 3 and the ultimate strength is 900 megapascal, Determine whether the bar is safe. Problem number 2. A material has an ultimate strength of 600 megapascal and a working stress limit of 120,000 kilopascal. Determine the factor of safety. So here is the solution of problem number 1. Step 1. We convert the load into a Newton. Step 2. We compute actual stress with a formula of stress equals force divided by area. Step 3. We compute working stress with a formula of working stress is equal to ultimate stress divided by factor of safety. So it means the bar is safe but exactly at the limit. There is no extra safety margin in case of unexpected loads. So here is the solution of problem number 2. First step, we convert working stress to megapascal. Step 2, we calculate factor of safety with a formula of factor of safety is equal ultimate stress over working stress. We have two sample problems of factor of safety. Problem number 1. A rod carries a load of 120 kilonewton and has a cross-sectional area of 400 millimeters squared. The ultimate strength of the material is 500 megapascal. Determine the factor of safety. Problem number 2. If the working stress is 75 megapascal and the required factor of safety is 3.2, determine the minimum ultimate strength. So here is the solution of problem number 1. First step, we converted the load. Step 2, we compute actual stress with a formula of stress is equal to force divided by area. Step 3, we calculate factor of safety with a formula of factor of safety is equal to ultimate of strength divided by actual stress. So here is the solution of problem number 2. We calculate the ultimate strength. We use a formula from the derived formula of factor of safety. Ultimate strength is equal to factor of safety times working strength. Working stress and factor of safety are directly related because working stress is obtained by dividing the material strength by the factor of safety. Increasing the factor of safety lowers the working stress, making it safer, while decreasing it raises the working stress, making it more efficient but less safe, so that the working stress and a factor of safety are connected. If the factor of safety increases, the working stress becomes smaller, making it safer. If the factor of safety decreases, the working stress becomes larger, which increases efficiency but also increases risk. Working stress defines the safe limit of stress, while the factor of safety provides extra protection. Together, they ensure that materials and structure remain safe, reliable, and durable over time. So, the working stress sets the safe limit of stress, while the factor of safety provides extra protection. Both concepts work together to keep materials safe and reliable during use. And that's all. Thank you.